All right, so the next topic that we're going to talk about is continuity. So for continuity, we're looking at a function at a particular point to determine if it is continuous or if it's not continuous. The three conditions for continuity are limit as x approaches c of f of x exists, f of c must exist, and the values for the limit as x approaches c of f of x must equal f of c. So this particular format could require that you figure out both the limits from the left and the right for a particular point, then determine that the limit is, as in general, exists from there, and then finding the value of the function and finally showing that they're equal. This also could apply to whole regions of the function. You may have a whole region which is continuous on an open interval. That would mean that each point on that open interval has this property where the limit exists, the function exists, and the values are equal. In general, you won't be proving on whole open sets because that's an infinite number of values that you'd have to test, but you'll be able to determine or you'll be given that a region is continuous and will be able to work from there. So continuity properties. So for particular functions, such as the constant function or functions which are a power term, you're able to say that those functions are continuous everywhere. So anytime that you have f of x equals k, which is a constant, for example, having f of x equaling 1, that would be continuous everywhere. If you have f of x equals x to the n, where n is an integer, for example, f of x equals x cubed, then you would have a function which is continuous everywhere in that case as well. Similarly, polynomial functions are all continuous everywhere. And the function f of x equals e to the x is continuous everywhere as well. This is an interesting function, which we'll see a lot more later on, but it's good to see it here and get some exposure to it, so that way it's not as foreign when we get to it later. Some stuff that's interesting about other functions which are not continuous everywhere are rational functions, which are continuous everywhere except for when the denominator is equal to 0. So setting that denominator polynomial to 0 and solving for those vertical asymptotes also determines areas where the function is not continuous. We also have that x to the n of, or x to the nth root, f of x to the nth root is continuous whenever f of x is continuous except for when n is even. And then in that case, it's only when f of x is continuous and it's non-negative. Part of the reason is because if you have an even root, you can't take negative or negative roots in that case, or can't do roots of negative values when n is even. So if you did, you would end up with some potential problems having to do with complex numbers and the imaginary values, which goes into a completely other class, but it's an interesting topic in and of itself. So if you're interested in complex analysis, that's one area to go, or what happens in this particular case. So, all right, that's the end of this one. So I'll see you guys next time.